Hello world, and welcome back to an introduction to artificial intelligence. So last time we took a look at how we can use AI to play games really well, games like tic-tac-toe or chess or Go. And today we're going to continue our exploration into AI and computers and the capabilities. And let's start by thinking about what it is that computers traditionally have been good at. If we think about what computers traditionally have been good at, we might think about things like performing calculations. That if you give a computer a math equation to solve, that computer can solve that math problem really, really quickly. Even if it's a complex math problem that would take humans much more time to calculate by hand, a computer can get the accurate answer very efficiently. You might also imagine examples like computers being a great tool for storing information. You can give computers large quantities of information, like every word in the English language and the corresponding definition, and then build something like a dictionary application, where you could type in a word into the computer, and the computer can very quickly give you the correct definition of these words. And so these are examples of what we might call deterministic uses of computers. Every time you plug in a math equation, you're always going to get the same answer. Every time you type in a word, you're always going to get the same definition. And you can feel confident that the computer is correct, that it will always give you the correct answer to whatever math equation you happen to throw at it. And so this is what computers traditionally have been very good at. But increasingly, we often want computers to be able to work in situations where they might not know the answer for sure, where they might have to guess, or they might have to make some kind of a prediction. But we still wanted them to be able to make a useful and hopefully mostly accurate prediction as well. So let's consider a couple of examples of that. Imagine, for example, on your mobile phone, you go to plug it in at night, and it tells you how much time it'll take until the phone is fully charged, for example. That estimate of the number of minutes it'll take in order for the phone to be fully charged is ultimately just an estimate. It's some number of minutes, and hopefully it's accurate, but it might not be exactly right. But even still, it's a useful prediction. Or, for example, maybe you get a phone call, and your phone predicts whether it thinks that phone call might be spam. Again, it's a guess. Hopefully it's right most of the time. It might not be right all of the time, but it's still a useful prediction for computers to be able to make. And so that's what today is going to be all about. Today is going to be all about AI making predictions. And we'll talk about the types of predictions that AI can make. And in particular, we'll look at the strategies that AI can use in order to make useful, valuable, and hopefully accurate predictions as well. So when we think about what it takes for an AI to make predictions, let's go ahead and pull up our AI here. Ultimately, what's happening is the AI is going to need something as input, and we'll talk in a moment about what that input might look like. And then as output, the AI is also going to produce something as output as well. And what goes in between this input and the output, is what we're going to start to call a model, or a machine learning model. And the idea of what a model is it's some representation of reality. It has some knowledge of reality that it's using to try and transform that input into that output. And I know that's a little bit abstract, but we'll go ahead and get concrete in just a moment. But what are the kinds of output that our machine learning model might produce? Well, sometimes that model might produce a number. Sometimes it's a number that we're trying to predict. And when we have a machine learning model that is predicting a number, we call that kind of problem a regression problem. And we'll talk today about some examples of kinds of regression problems and how AI can try to solve them. And meanwhile, sometimes we have a model where instead of predicting a number, we're predicting a category. We're trying to group some data into a bunch of categories. And this kind of problem we then call a classification problem, a slightly different kind of prediction. But today is going to be all about exploring both of these kinds of predictions, both regression-type problems and classification-type problems. And let's go ahead and start with regression. And remember that regression is this idea that we have a computer, we have some AI, and we want it to make a prediction. And the thing we want it to predict is some number, ultimately, that we want it to predict some numeric value. So what might that look like? I'll give you a couple of examples. We talked already about the example of plugging in your phone and seeing how many minutes it'll take until it's fully charged. That number of minutes is the output of some kind of a prediction model. We're trying to make some prediction as to how long we think it's going to take to charge the device. And ultimately, your phone is predicting some number of minutes as a result. Other examples might be you go ahead and go on a workout, and maybe your phone or your watch or your fitness tracker is tracking your workout. And at the end, it tells you how many steps you walked. And it might not know for sure exactly how many steps you walked, but hopefully it can make a pretty good prediction. Again, the thing that it's predicting in this case is a number representing the number of steps that you took. Or alternatively, maybe you're downloading a file from the internet and you see an estimate of how many minutes are remaining in that download. That again is a prediction. Just because it says there are 9 minutes remaining, maybe it'll take 8 minutes or 10 minutes or a little bit more. But again, we're predicting some number, like a number of minutes remaining, and we hopefully want our AI to be able to make a good prediction. So those are regression types of problems, where we're predicting a number. Meanwhile, we also have another kind of prediction that we called classification. And the idea of classification is instead of predicting a number, we're predicting some kind of category. Anytime we're trying to group some piece of data into one of multiple different categories, we call that classification. And so examples of that might be you get a phone call. We talked about this example a moment ago, and your phone either has to decide for that given phone call, do I think this is a normal phone call, or do I think this is likely to be spam? And so we're grouping every phone call into one of these two categories, or one of these two classes, hence the name classification. Meanwhile, we could look at other examples. Examples like maybe your phone has a face sensor, so you can unlock your phone via your face. Well, then when the phone sees your face as input, it needs to make a classification judgment. It needs to decide, is that face your face, or is it someone else's face? Is it an authorized user who should be able to unlock the phone, or is it not? That's a classification problem where we need to group that piece of data into, in this case, one of two categories. Or alternatively, maybe you get a text message, and on some phones nowadays, they can classify some text messages as particularly important, or like a priority notification for you, to let you know this is a message you particularly want to pay attention to. This, too, is just a guess. It's making a prediction as to whether we think this text message is a normal text message, or particularly important, or maybe automatically classifying some text messages as spam. But once again, we're taking some input and trying to decide what category of output does it belong in. And so these kinds of predictions are the kinds of things we'll be exploring today, and thinking about how it is that we can get AI to make good predictions by taking an input, processing it, and ultimately producing some kind of useful predictive output. So let's start then by talking about how AI can solve these regression problems, where the idea of a regression problem, again, is what we're doing is predicting a number. We'll go ahead and give you an example. Imagine that we have our AI here, and we have our AI trying to grow some plants. And so we've got some plants that happen to be growing here. And we might imagine that what we might want to predict is how much do the plants grow. That might be some number that we're trying to predict. How many inches or centimeters are our plants going to grow? But then we have to think about, all right, what is the input to the problem? What is the piece of information we're using to try and predict how much our plants are going to grow? What is the variable that is going to affect how much our plants are going to grow? And one variable you might guess might be, oh, the amount of sunlight. You might imagine that if there's more sunlight, well, then our plants are going to grow a little bit more. And so now we frame this problem as a bit of an input and output problem, where the input is the amount of sunlight, and the output is how much our plants are going to grow. So we could try to represent that via some diagram. We have some amount of sunlight that we'll go ahead and represent here. We'll go ahead and put a number in here. This is just arbitrary. In some units, for example, we have some amount of sunlight. And from there, we're going to try and predict some amount of plant growth, how much plant growth is going to correspond to what amount of sunlight in whatever units we happen to choose. And the idea we expect is that as you increase the amount of sunlight, well, then likely what we should expect is we should expect an increase in the amount of plant growth as well, that there should be some kind of a relationship between the input and the output. And we don't know exactly by how much the output is going to increase when we adjust the input, but hopefully we have some sense that what we want AI to do is understand the relationship between these two things, between some input number and some output number. And the same is going to be true for other kind of regression problems that we could come up with as well. Maybe the input is the battery life, and the output is the amount of time it's going to take to charge our phone, where if our battery is already mostly full, if our battery level is very high, well, then it's probably going to take a little bit less time to charge the phone. Whereas if our battery is almost dead, then it's going to take some more time to charge the phone as well. So one number being used to predict another number. You could imagine doing the same thing for, depending on how much distance you covered, then you might try to have your workout app or your fitness tracker predict how many steps you took, for example, or depending on the file size of the file that you're trying to download from the internet, you might use that information to try and predict what the download time ultimately is going to be. So we have this problem now framed as this input-output mapping. We have some input number that we're using to try and predict some output number. But how then does AI go about even trying to make this kind of prediction? If I tell the AI, here's the amount of sunlight, how much will my plants grow? Or here's my file size, how much time is it going to take to download that file? it's going to be difficult without giving the AI some additional information for the AI to make a good prediction. It doesn't have a lot of information to work with. And so what we need to do is we need to give the AI some data, some information that it can use to help it make these kinds of predictions. So let's go ahead and give the AI some examples of some data. So here's an example of a piece of data that we might give to the AI, where we might say that based on past experience, based on existing information, we know that if the input is 2, in this case, the output was 4 for one of these regression type problems, where we're using an input number to try and predict some output number. And usually one data point's not enough. Usually we want a collection of data, a whole bunch of data to use to be able to train AI to understand this kind of prediction. And so we might have another data point. Say the input is 3, and in that case, the output was 6. And maybe another example where the input was 7, and the output was 8. And we'll go ahead and add one more data point as well. This is what we then call training data. And ultimately, a lot of AI needs training data in order to be able to learn something useful. That AI needs some information about the world in order to use that information to train its own model, so that it understands the relationship between real things in the world to be able to know how to make some kind of a good prediction. So we give the AI all of this training data and hope the AI can do something useful with that training data to be able to identify patterns, to be able to understand something about the relationship between all of the information that happens to exist in this training data. So what could we do with the training data? Well, one thing we could do, since these are numbers, is we could represent them visually. We could draw them on a graph, for example. So here I've got this graph with an x-axis going left and right here, and a y-axis going up and down here. And I could take each one of my training data points and plot it on this graph, where this data point, where the input is 2 and the output is 4, the input will go ahead and represent along this x-axis going left and right here. And the output will represent along the y-axis going up and down. And so if the input is 2 and the output is 4, well, then we'll go ahead and go 2 across along this x-axis, and we'll go up 4 along the y-axis, and we can put a data point there. And likewise, for the input being 3 and the output being 6, we can do the same thing. Take the input of 3, go up 6, plot that data point there as well, and then do the same for the remaining 2 data points. And now we have some visual representation of this data that we as humans can take a look at and try and use to understand this relationship. And hopefully, looking at this relationship visually, you can get the sense that for most of the data points, it seems like as we increase the input value, then we also increase the output value. That as we increase the input value along the x-axis, the values are also getting higher. And so we see this kind of positive correlation between these values. But it's also possible that for a different set of data, for a different problem, we would have seen a negative correlation, where instead this slope would go downward instead of upward. Or maybe there'd be no correlation at all, and we'd have to come up with some better strategy for how we're going to try and make these kinds of predictions. But by looking at the data visually, we can start to get a sense for how we can try and make these kinds of predictions. So let's go ahead and take a look at some examples of what it might look like to plot data, and then what it'll look like to try and infer some kind of relationship from that data and understand how we might make predictions based on that data too. And so like we have, and then the y-axis here going up and down would represent plant growth. And so then I need to populate this graph with some training data, some information about past plants that I've grown, where I've maybe recorded how much sunlight they got and how much they grew, for example. And so each one of these points here represents some piece of training data that I have from experience that I'm now trying to learn from. And as I move it left and right, if I move it further left along this x-axis, left and right, this represents less sunlight. As I move it to the right, that represents more sunlight. And then moving it up and down represents how much that plant grew. If the point is further down, that means the plant didn't grow as much. If the point is further up, that means that the plant grew a little bit more. And so ideally, I have not just one, but multiple pieces of training data. And with all of that training data, the goal then is to understand something about the relationship between these points, where the idea might be that as the x value increases, as the amount of sunlight increases, the amount the plant grows will increase too. And I want to use this information ultimately to make a prediction, not just about the training data, but about new data, where if I were to encounter some new plant in the future and say, here is the amount of sunlight that it got, I want to be able to predict how much that plant ultimately will grow. And I could do that by saying, well, I have these existing points, and I could use these points ultimately to try to draw a line that hopefully represents the relationship between all of these points. And in this case, the points are already pretty close to being in a line already. But usually that's not going to be the case in the real world, that data is going to be a little bit messy. It might not be perfectly in a straight line all the time. But hopefully you can see that even though this data isn't perfectly in a straight line, there's still some kind of a relationship here, that as we increase one value, the other value is increasing too. So you could imagine me trying to draw a line that kind of approximately models this relationship. Again, we're using this word model to describe the relationship between these two values. And what can I do now that I have this line? Well, I can use that line to make new predictions, where if in the future I say, here is the amount of sunlight that a plant got, maybe it got, say, like this amount of sunlight, I can say, all right, well, where does it fall along the line? I can go up and find, all right, it falls right about here on that line. And so I can predict that about this is going to be about how much that plant is going to grow. So by drawing this line, we can understand the relationship between these two values, and I can make a prediction. The prediction might not totally be right. You notice all of these data points don't fall directly on the line, but hopefully they're at least close to the line. And as a result, I can make some pretty accurate predictions about how to understand the relationship between these two values. So now let's take a look at how we could then feed this information to a computer, so a computer could hopefully draw a line better than the one that I found, hopefully find an even better one that can make even more accurate predictions. So this process where we take a whole bunch of training data and then we try to draw a line that represents the relationship between these data points is what we call linear regression. It's a way of solving a regression problem by, in this case, drawing a line that represents the relationship between those two variables. And let's take a look at how it is that a computer could try and solve a linear regression problem. So we'll go ahead and draw some axes here, create another graph, and we'll put a whole bunch of data points here on that graph. And you might imagine that now we might want to try and draw a line that represents these data points. And I could draw a line that looks something like this, for example. But there are many possible lines that I could draw. Some of them are going to be better than others. Some of them are obviously bad. For example, if I were to draw a line like this, well, that clearly doesn't capture the relationship between these data points. In one sense, this line is going down, whereas the data points seem to be going up, for example. But there are a lot of lines that look like they could be reasonable. For example, this line looks OK. It looks like it does a pretty good job of going up along with the data. But there's also this line. Is that a better one? Maybe it's closer to some data points, but maybe it's further away from some others. It's a little bit hard to tell. This one looks pretty good, too. It's kind of in between some of them. But which one is the best one? We need some way of evaluating, if we're using this line to make predictions, how good or bad are our predictions. And the way we can do that is by taking our line and really trying to estimate, how good or bad was it based on the training data. The training data is the information we have to work with. And so we're going to use that training data to try and figure out how good or bad our model happened to be. And so what we're going to construct is what we call a loss function. Our loss function is going to estimate and tell us how good or bad our prediction is. And so what does that look like? Well, let's go ahead and draw a graph again. And let's imagine that this is our prediction. And let's say that this is our real piece of data, our real data point that we were using to try and inform the way we make that prediction. And we're going to call that data point y, representing how high up or down that data point is. And our line made a prediction for that value. The prediction that our line is making is if you go to the same x value, the same place left and right along this data point, and say where along the line does it fall, our prediction is this point here. It's a little bit lower, but it's the point that's actually on this line. And that prediction we usually call y hat. Y hat because it's y with this kind of hat-looking shape on top of the y. And so based on these two data points, y, the real piece of data, and y hat, which was our prediction, we have some sense for how far away are these 2 points. And that's going to tell us how good or bad is our prediction. If our prediction is good, ideally these 2 points are close together. And if our prediction is bad, then these 2 points are going to be a little bit further away. And so this distance, the distance between y and y hat, represents something about how wrong our prediction happened to be. And there are a couple of ways we could measure this via a loss function. One way is to use what we call the absolute error. What the absolute error is we take these 2 values and we just subtract them from each other. We say y hat minus the y value. And then we take the absolute value. And if you're unfamiliar, these vertical lines called the absolute value just mean make sure the number is not negative. So it doesn't really matter if we're off in one direction or the other direction. We just care how far away are we. And so that's the absolute error. How far away are these 2 data points? There are also other kinds of error that we could consider too. Another popular kind is the squared error, where you take the distance between these 2 points and you multiply it by itself. And you do that for a couple of reasons. One thing is that it also makes sure that the value is never negative. When you multiply a number by itself, you're not going to get a negative number as a result. And ultimately, there are some other mathematical advantages too. Some of them are related to the fact that when you square the error, you end up punishing the really wrong answers even more. That if you had something that had, say, that was maybe 3 away, so the absolute error was 3, well, then the squared error is going to be 3 times 3, or 9. And so as the error increases, the squared error increases by a lot. And so as a result, we really punish cases where we're further and further away from what the prediction was supposed to be. And so we have a few different choices for how we formulate that kind of problem. And when we're calculating the error, usually we're not doing so just for a single data point. Usually we're doing so across multiple data points. We have a whole bunch of training data, not just one piece of data, but many. And across all of those pieces of training data, we might say, what is the absolute error or what is the squared error across all of those data points? And then we could calculate something like the mean squared error, where mean in this case means the average. So the average of all of the squared errors across all of those data points. And that's going to give us some sense for how bad is this particular prediction line? How well or how poorly is it making predictions? And then what we could have a computer do is try and find the line that minimizes the mean squared error. Remember that last time we talked about the fact that computers are really good at working with numbers and optimizing those numbers, trying to make some value as big as possible or make some value as small as possible. And now we've got some value that we can try to optimize. We can say this mean squared error represents how good or bad our prediction line happens to be. And so what we should tell the computer to do is try to find the line that minimizes that mean squared error, that makes the mean squared error as small as possible. And by making it as small as possible, we can hopefully get the most accurate predictions as a result. And in doing so, we could solve problems like taking some amount of sunlight and then calculating how much plants are going to grow. Now, so far as we've been thinking about these regression problems, we've been thinking about them in terms of one input variable and then one output variable, where the input, say, is the amount of sunlight, and the output, say, is how much the plant is going to grow. But the real world is often more complicated than just that. Often it's not just one piece of input information that's leading to the output. There are lots of different factors that can affect how much a plant is going to grow. For example, you might also want to take into consideration how many nutrients that plant happened to get. And so often we'll have multiple different inputs that are being used to predict that output. And ideally, with multiple inputs, we can do a better, more accurate job of trying to predict whatever the output value happens to be. And we could do that for other problems too. If we were trying to predict how much time it's going to take to charge our phone, for example, you might try and predict that not only based on the battery level, but maybe also based on the temperature, whether it's really hot or really cold outside. That can affect how easily that battery can be charged. And so maybe that's a useful piece of information for calculating how long it's going to take to charge the battery. Or if we're trying to calculate how many steps you took on your workout, maybe we want to consider not only how far you traveled, not only your distance, but also your speed. How fast were you going, for example? Or if we want to calculate how long it's going to take to download a file, well, that depends not just on the file size, but also on your internet speed. That's going to be another factor that we need to take into consideration too. And so we can increase the scope of these regression problems and say, don't just use one input variable, but use 2 or 3 or 4 or many different input variables, all to try and predict this output value that we're ultimately interested in. But essentially, even across multiple variables, it boils down to the same idea of trying to see where these points fall and then trying to understand the relationship between those points. And as we add more data, we can get a better sense of that relationship. As I increase the amount of training data that I have access to, I increase the information that I can use, and hopefully can get a better, more accurate sense for the relationship between these data points as well. So those are some of the ideas behind how we can use computers and AI to be able to solve these regression problems, taking information, taking training data, and using them to build this regression model that's able to make predictions and ultimately predict a number. But remember, regression was one of the kinds of predictions that we were interested in. The other kind we were interested in was this idea of classification, where we're not necessarily trying to predict a number, but instead we're trying to categorize things. We're trying to put things in one category or another, grouping phone calls into spam and not spam, for example. And categorization is something we all do all the time. We're constantly faced with choices in our lives where we have information around us, and we need to group it into one category or another. For example, you might have encountered situations where you're packing for a trip or you're moving, for example, and you've got a whole bunch of clothes, and maybe you need to categorize those clothes into different categories, into your shirts and your pants, or into your summer clothing and your winter clothing. And so we can use this then as an example of a type of classification problem, where we need to decide for any given piece of clothing, what category does it fall into. So let's take a look at an example of that now to see what classification might look like in practice. So I have here some clothing, and you might imagine that I want to now sort that clothing into different categories. For example, I have a box here for summer clothing, and I have a box here for winter clothing. And this is an example of a classification problem. I have my inputs. My inputs are each of these various different articles of clothing. And my output is going to be what category, what class does that piece of clothing fall into? Does it belong in the summer box, or does it belong in the winter box, for example? And so we might try to solve this kind of classification problem by going through the articles of clothing and say, all right, this here looks like it's probably an article of winter clothing. So I'll go ahead and put that into the winter box. And this here looks like it's probably a piece of summer clothing, so I'll go ahead and put that into the summer box. But what we can start to ask ourselves is, how are we making that decision? What information about the input data are we using to decide if it belongs in the summer box or if it belongs in the winter box? And so I could take an article of clothing here, and you would probably say this probably looks like a piece of summer clothing. It probably belongs in this box here. But why? And there are lots of different features, lots of different characteristics of this piece of input data that I might use to make that judgment. Maybe I'm looking at the thickness of the fabric, and this looks like a pretty thin piece of fabric. So maybe thinner pieces of fabric are a better fit for summer, and thicker pieces of fabric are a better fit for the winter. Maybe it's something to do with the patterns. Like this looks like a bit of a summery type of pattern, and so maybe that means it belongs in the summer box. Maybe I'm looking at the length of the sleeve. Seems like a reasonable judgment. If this is a short sleeve, then maybe that's better for summer and otherwise for winter. And we could try that. We could base it on the sleeve length and say, short sleeve, we'll go ahead and put that into the summer box. And if I had another article of clothing where the sleeves were longer, well, then maybe that belongs in the winter box. So this seems like a pretty good rule, a pretty good algorithm for us to use for doing this kind of classification. But then maybe we look at this article of clothing where the sleeves are very short, this vest here. And so by that logic, maybe it should be an article of summer clothing. But this material, it's got some weight to it. So maybe this would keep me warm in the winter. So maybe it deserves to be in the winter box. And it might be a little bit ambiguous as to how you might make that decision. But maybe our rule needs to be revised a little bit. If you decide, you know what, maybe this belongs in the winter clothing box, then maybe I need to make some adjustments to my rule as well. Likewise here, I've got a article of clothing with some longer sleeves, and so maybe you might say it's a better fit for winter, but this material is pretty thin, and so maybe it's instead going to be something that might be used on a summer day where it's not too hot, for example. And so the problem can get a little bit more challenging too. Sometimes it's going to be more obvious what category some article of clothing falls into, and sometimes it's going to be a little bit less obvious too. But the goal then is to give this information to a computer, or we can give the computer some examples of data and say, here are some examples of data that fall into this box, and here's some examples of data that fall into that box, and let the computer figure out on its own some kind of useful rule that it can use to figure out what box that particular piece of input belongs in. And so that's the idea that we're going to be exploring as we think about how to get a computer to be able to classify data well. So classification can be used to solve lots of kinds of problems. One common type of prediction you might make is maybe about the weather, for example. If we want to go back to our example of our AI that's trying to grow some plants, for instance, if we are trying to grow plants, one thing we might care about is knowing whether or not it's going to rain, for instance. Because on a rainy day, that might affect how much water our plants get. It might affect the choices and the decisions that we happen to make. And so one thing that might be useful for us to do is for any given date, predict whether or not it's going to rain or not on that date. And that, too, is an example of a classification problem, where I have some date, I want to predict if it's going to be rainy or not rainy. And just as in the clothing example, where we took an article of clothing and we put it into one of two boxes, either the summer box or the winter box, you might imagine that what a computer might want to do, what our AI might choose to try to solve, is take a given date and then figure out, does that date belong in the box that corresponds to rainy days, or does it belong in the box that corresponds to not rainy days? This is the classification problem that we're trying to solve, is decide, does it belong in box number 1 or does it belong in box number 2? And maybe based on this particular date, we say that, you know what, that date, we predict it's going to rain on this date, but on some other date, maybe we predict that it's not going to be raining, for example. So this is the general setup of our classification problem, where we're trying to divide things into categories. We're taking input. We're deciding if it's rain or no rain. We're deciding if it's a spam phone call or if it's not a spam phone call. If the user trying to unlock your phone is an authorized user, or maybe that user is not authorized to unlock the phone. Or if a text message you get is an important notification or not an important notification. All of these are examples of classification problems, where we have some input data and we need to decide what category does it belong in. And in order to do that, we need to use our input data. We need to say, given all of this existing data, where I have data about past days and whether it rained on that day or whether it didn't rain on that day, ideally there's something in that information that I can use to decide which category I think that piece of data belongs in. And so what kind of data might I use? Well, given a date, there's lots of information that I might use to help me predict whether I think it's going to rain on that date or not. For example, I might use the temperature. That might be one important factor that I consider when determining whether it's raining or not. Maybe I use the amount of air pressure, because I know that that can sometimes affect whether it's going to rain. Maybe the cloud cover. If there are more clouds in the sky, that can be an indication that there might be some amount of rain there too. And the humidity, the amount of moisture in the air, that matters for determining if I'm going to predict whether it's going to rain. So all of these are variables that I might use to try to predict whether I think that day is going to be a rainy day or a not rainy day. And all of these individual pieces of information are what we then call features. These are features of my input data, that if I have all of this training data, that training data is going to tell me on this particular day, here was the temperature, here was the air pressure, here was the cloud cover, here was the humidity, and here is a description of, for all of that information, did it rain or not on that day. And hopefully by using lots of examples of data of this form, I can learn from that. I can ultimately learn some kind of calculation that our AI can use to take all of this information and make some kind of a prediction for whether it's going to rain, to be able to say that, yes, on this day, it's going to rain. And maybe for some different day, we might say, you know what, no, it's not going to rain. And we're doing that same calculation based on whatever input data we happen to have. And so this then is the goal of classification, to take all of these features and have our AI learn from those features, learn from the training data, and come up with some kind of pattern that we can use to predict whether or not we think it's going to rain. But how then does that work? If we have all this data, how could we use that information inside of a machine learning model so that AI can make good predictions? Well, there are lots of different algorithms we could choose for trying to make predictions, and we'll look at a couple of them today. Let's start with an example that initially will just use a single variable. Imagine that we're trying to use air pressure to decide whether or not the date is rainy or not rainy. And you imagine that this is a axis going left to right, where on the left represents data points where the air pressure is very low, and on the right represents data points where the air pressure is very high. And what we need is some example data, because right now I don't know, how does air pressure relate to whether or not it's going to rain? And so let's take an example of a data point from a rainy day. I'll color it in blue to represent the rain. And it had this amount of air pressure, and this is a data point in our training data representing a rainy day. And let's add some more data points. Here's a data point from a day that was not raining. So it wasn't raining, and the air pressure is a little bit higher. And so maybe I'm starting to learn something about the pattern, the relationship between air pressure and rain by looking at data like this. But 2 data points is not very much. Ideally, I have more data that I can use to try and make these kinds of decisions. And so let's add a little bit more training data to my example here. And maybe now I'm starting to notice a pattern But let's now say that I want to predict data about the future. This is all data about the past, where I have historical data for air pressure in the past, and did it rain or not on those particular days. And now imagine in a future day, I know what the air pressure is. The air pressure is this value here. And the question is it a rainy day? Is it going to be a blue dot? Or is it a not rainy day? Is it a day that's going to be a red dot instead? And if we look at this data, and you look at it too, do you think it belongs as a blue dot, or do you think it belongs as a red dot? I'd say it probably belongs as a red dot. And why did I make that decision? Why did that seem to be the instinct that I came to? Well, one thing you might say is well, this data point was really close to this red dot over here. So if this data point had this amount of air pressure and it was a red dot, meaning not a rainy day, then this other point, which was really close to that red dot, probably should be a red dot as well. And so this is actually an algorithm. It's an algorithm called nearest neighbor classification. And the way nearest neighbor classification works is if I have a whole bunch of training data, then I can say for any new data point, some new data point that I have to work with, I can say, what is the data point that it looks closest to? What is the data point that had the closest air pressure to that new data point that I'm looking at now? And for that existing training data point that it was closest to, was it raining or was it not raining? And that can tell me some kind of a prediction. And that seems like a reasonable way to predict, because if it looks close to a date that wasn't raining, then it's probably a fair guess that it's not going to be a rainy day. And so nearest neighbor classification is a popular tool that we can use for very simply making these kinds of predictions. And meanwhile, if I had another data point that was right here, for example, with this amount of air pressure, what nearest neighbor classification would say is it would say, OK, well, the closest neighbor is this point right here. And that data point is a blue data point representing a rainy day. So what I'm going to predict for this new data point is that it probably also deserves to be a blue dot. It probably also should be predicted as a rainy day. Now, sometimes data isn't as clean as this. Right now, I have this very clean data where all the blue points are on one side and all the red points are on the other side. And so it's very easy for me to try and say one conclusion or the other based on what side it happens to fall on. But real-world data is complicated. Real-world data is messy. Maybe we're going to have some outliers, some data points that don't necessarily fall clearly on one side or another. And so maybe I have an outlier, a rainy day that did actually have higher air pressure for some reason, or it could be some other example of something that we're trying to classify. And imagine now that I gave you a new data point to try and make a prediction about. And I said, this data point over here, over to the right, should that be a blue data point or should it be a red data point? And you could look at it yourself. You could try to make a guess. On one hand, the closest data point to it is this blue data point here. And so according to the rules of nearest neighbor classification, we might say that this new data point 2 should be considered a blue point. But on the other hand, it's close to a lot of other red data points. And so it might also be reasonable to say, you know what, I think that data point should be red. And so often, rather than say, nearest neighbor classification would call this blue, but maybe we would rather call it some other color, maybe we'd rather call it red, we could adapt this algorithm slightly. Rather than just use nearest neighbor classification, we can use an algorithm that we call k nearest neighbor classification, where the idea is that instead of just looking at the 1 nearest neighbor, we look at maybe the 3 nearest neighbors, or the 5 nearest neighbors, or k nearest neighbors, where we choose some value for k, some value for how many nearest neighbors do we want to look at. And we look at all of them rather than just one. And we could say, well, if we look at the 3 nearest neighbors, 2 of them were red, only 1 of them was blue. And so balance of probability, maybe I say that this data point deserves to be red instead. And so we can use these adjustments, these kinds of k nearest neighbor classification algorithms, to be able to hopefully make some pretty good predictions as to what category some piece of data belongs in. And so far, we did that for just a single variable. But nearest neighbor classification works even if I have multiple variables, too. If I want to consider not just air pressure, for example, but maybe I want to consider both air pressure and humidity and use that information to decide, is it going to be a blue point, a rainy day, or is it going to be a red point, a not rainy day, for example? Then I could plot that in 2-dimensional space and then say, using both of these features, given some new data point, which other data point is it closest to? And we could do that in even more dimensions, too. As I add more different features, as I consider more different input variables, we could continue to imagine how you might find the nearest neighbor. And even though we humans usually think in either 2 dimensions or 3 dimensions because we live in our 3-dimensional world of left and right and forward and backward and up and down, computers have no trouble imagining even more dimensions than just 2 dimensions or 3 dimensions. Computers can think in even larger dimensional spaces, so to speak, because to a computer's perspective, each dimension is just a number. The humidity is just a number. The air pressure is just a number. So adding 4 or 5 or 6 dimensions, even though we have a hard time imagining what 6 dimensions might look like, a computer can deal with that okay. So nearest neighbor classification, that's one possible way we can use to try and solve these classification problems. But there are lots of different algorithms that we can use to solve classification problems too. And one of the most popular is, in fact, inspired by the human brain. And it's something that we call a neural network. And neural networks show up all the time in AI, not just in classification, but in regression and other kinds of AI-related problems as well. And so I want to take some time today now to talk about what really is a neural network. What is it doing, and how is it that neural networks are solving these kinds of problems, and what is AI doing when it's using a neural network? And the idea of a neural network is it's based on the human brain. So the human brain has neurons. They look a little something like this. And importantly, we have many neurons that are connected to each other. So you imagine neurons that are connected to each other and that pass information from one to the other, that each neuron has some like electrical stimulus, and they can pass that electrical signal from one neuron to another neuron. And so the idea then was to say, well, if our neurons are connected to each other and via their connections and via the way they pass information from one neuron to the next, that seems to be able to solve a lot of complicated problems. And could we try to build a computer? Could we try to design AI that's built on similar kinds of ideas, similar kinds of principles, so that we could use that technique to be able to construct not a biological neural network, but an artificial neural network? Or you might imagine that instead of a biological neuron, we have an artificial neuron. And so an artificial neuron is going to be something built into the computer. You might imagine it as just one of these units that instead of storing some biological electric signal, maybe just instead stores some value, some number, maybe representing some electrical signal or something else. But this value, maybe it's 0, meaning like it's off, or maybe it's 1, meaning like it's on, or it has activation, or maybe it's some value in between. It might be some other value, some value with a decimal point after it. But we have these artificial neurons, which are neurons that exist only in the sense that they exist inside of the computer. And what we can then do is connect these neurons to each other. That rather than just have a single artificial neuron, we can connect these artificial neurons to each other just like biological neurons are connected to each other. And in the end, construct something that we might call an artificial neural network. I'll take a brief break, get some water, and then pick up from here. So what does an artificial neural network actually look like? Well, we can take these artificial neurons, connect them to each other, and maybe I'll draw an example for you of what an artificial neural network might look like. So I have here a blackboard. And remember, these circular units, these represent the neurons that we might call neurons. We sometimes call them units of our artificial neural network. And so I'll go ahead and put one neuron over here. And then we'll go ahead and take another neuron that we're going to connect this neuron to. And so here now then are two artificial neurons. Put them here and here. And we'll go ahead and connect them to each other. And by connecting them to each other, the idea that we're saying here is that whatever information is stored inside of this neuron here on the left, you can imagine the information flowing from left to right, that maybe this neuron has some value, maybe some electrical signal, so to speak, and it's going to pass that signal on into this output neuron as well. So the output neuron's value, the information that it stores, the number that it stores inside of this neuron, will be based on whatever this input happened to be. And in practice, we don't just have two neurons that are connected to each other. We often have many more. So let me go ahead and add a couple more neurons here as well. And in this case, we might connect each of these neurons to this neuron on the right. And so when I draw a diagram like this, what we have here on the left side are what we might call the input neurons, that each of these neurons stores some kind of a value. They store some kind of a number. And we're going to use these input neurons to try and predict some value for this output neuron that we have over here on the right. That maybe what we want to do is try and make some kind of prediction, like is this date going to be rainy or not rainy, for example. And so based on all of this input information, we might use that input information to calculate the output. And maybe the output is going to be 1 if the day is going to be rainy, and maybe the output is going to be 0 if the day is going to be not raining, for example. And so what we want the computer to do is figure out how should we understand the relationship between all of these neurons. How should we try and connect the input neurons to the output so that we can make some kind of a good judgment as to what we think the output is going to be. So it's structured a little bit like the human brain, but we're going to look at some algorithms that computers can use to deal with neurons in this structure to figure out how to be able to calculate some kind of a good prediction. So let's walk through those steps now and think about what that algorithm actually looks like. So as we think about artificial neural networks, what we might imagine is in our rain example, maybe we have 4 input neurons that I'm drawing over here along the left side, where those 4 input neurons correspond to our 4 features, the features of the day that we care about that we're going to use to try and predict whether it's going to be raining or not raining. So we have features like the temperature and the air pressure and the cloud cover and the humidity. So here are my 4 input neurons. And what I want to do is I want to predict a single output neuron. I want to be able to predict whether it's going to rain or not. And so all of my input neurons are then going to be connected to the output. And the output, I want to be a 0 when it's not raining. And maybe if these data points were a little bit different, if the data points were data points that looked more like a rainy day, well, then I want the output to be 1 if it's going to be a rainy day. And so the way we formulate the problem then is for any given day, I should be able to pass in the temperature, the air pressure, cloud cover, and humidity into these input neurons. And what I want my neural network to do is understand how these neurons should be connected to each other. In other words, how to calculate the output based on all of these individual input neurons. And we need some way to calculate the output based on all of the input. So how are we going to do that? Well, to do that, we're going to introduce a little bit of math to talk about what is the math the computer is actually doing in order to determine what the value of the output neuron should be. So we had our 4 input neurons that before were things like temperature and cloud cover and so forth. But this generalizes not just to the problem of predicting whether it's going to rain. So instead, I'm going to label each of my 4 input neurons with just a variable name. I'm going to call the first one x1, and then x2, and then x3, and x4. And the output, which before was like rain or not rain, is again just a number, some number that I'm trying to predict. And so we'll call that number y in this case. And so what we want to do is figure out how do we calculate a value of y by combining all of the information from x1 and x2 and x3 and x4, for example. Well, how could we do that? How could we combine 4 values together? Well, the simplest way to combine 4 values together might be, say, to add them all together. And so here's one way I could combine all of my values. I could just add x1 plus x2 plus x3 plus x4. And that's a way to combine all these values and figure out what the value of y is going to be. But that's probably not going to do a great job of predicting what I want the value of y to be, because each of my 4 variables might represent something different, that depending on what the air pressure is, increasing the air pressure might have some effect on whether it's going to rain, but increasing the temperature might have a different effect, a different sized effect, a different direction effect, or something like that. And so it's not usually enough just to add all these values together. I want to understand the relationship between each input value and the output. When I change x1, how should that change the output? When I change x2, how should that change the output? When I change x3, how should that change the output? And so on for x4 as well. And so what would that look like? Well, we need to add to this story. We can't just say the only values we're dealing with are my input values and my output values. I need to understand something about the relationship between neurons that are connected to each other. And those relationships we're going to represent using a new variable that we call a weight. A weight represents the relationship between one neuron and another neuron. And so here I have weight number 1 represented as this variable w1, w2, w3, and w4. And these weights, again, are just numbers. And they're going to represent, when I change one of the inputs, how much and in what direction should the output change as well. And so what does that equation look like? How am I then calculating the value of y? Well, I'm going to take each of the inputs, and instead of just adding together x1 plus x2 plus x3 plus x4, I'm going to take each input value and multiply it by its weight first. So that by multiplying it by the weight, if the weight is really big, that means the input can have a big impact on the output. And if the weight is really small, it'll have less of an impact on the output. If the weight is positive, that means increasing one of the input values will increase the output value too. And if the weight is negative, well, then increasing the input value might decrease the output value instead. And so now the equation I have is multiply weight 1 by input number 1, and then multiply weight 2 by input number 2, and the same for input 3, and the same for input 4, and then add all of those results together too. And that way, these weights ideally can represent information that our AI is going to learn about the relationship between each of the inputs and what the output value is too. And oftentimes, we might have information about the output value that doesn't depend on any of the input values. Maybe you just know in general that you're in a city that happens to rain a lot, for example, regardless of what any of these input parameters are. And so sometimes we also have this additional value that we call a bias, which biases the output in one direction or the other that doesn't depend on any of the inputs. It's just an additional value that we add on at the end. But these weights and biases, these are the things that a neural network is learning when you train a neural network. Anytime you hear people talk about training AI, training a machine learning model, training a neural network, this is the kind of thing they're talking about. They're talking about maybe building a neural network and then telling the AI, you know what, figure out what the values of weight 1, weight 2, weight 3, weight 4, and that bias should be, so that this equation does a good job of calculating whether it's going to rain or not, or whether a phone call is spam or not, or any of these other different kinds of classification problems we might be trying to solve. That what a neural network, what an AI is learning, is it's learning the values that we should use for these weights and for that bias. And the weights and bias together we call the parameters of the model. These are the parameters that AI is learning. And so if you hear talk about machine learning models with many different parameters, what is a parameter? A parameter really is just some number that our AI is learning that it's using as part of this equation to be able to make some kind of a good or useful prediction. That parameter is just being used as part of the machine learning model to be able to make good predictions, and it's informed ultimately by the training data that it has access to. So let's take a look at a simple example and walk through what the actual calculation looks like from the perspective of a neural network. So we'll have a simple neural network that in this case has 2 inputs, and we'll have 1 output. And so each of the inputs will then be connected to that 1 output. And remember, each of these connections is defined by some weight, some number that represents that connection between the input and the output. And so in this case, we'll have this first connection have a weight of 1, and the second connection over here have a weight of 2. And then we'll add in a bias. That bias will have a value of 3 going into that output neuron as well. And so then the question is, what does this calculation look like? What happens when I give this neural network some input and ask it to perform some classification, to be able to classify something as like yes or no, for instance? And so we'll go ahead and give our neural network some input. We'll give it an input of 4 and an input of 5. And then we'll tell the neural network to perform its calculation. And what does it mean for the neural network to run? Ultimately, it's just going to go through that same mathematical equation that we talked about a moment ago. We're going to take each input and multiply it by its weight. So we take the input of 4, we multiply it by its weight of 1, and that gives us 4. And then we take the other input, this input 5, multiply it by its weight is 2. 5 times 2 is 10. And then we'll go ahead and add up those results and also add in that bias value of 3, which doesn't depend on any of the inputs. So we add together 4 plus 10 plus 3. We get an answer of 17. And then in the world of classification, where in this case I'm trying to do what's called a binary classification, just classify things into one of two categories, what I might do is I might take that output value and I might ask, is it at least 0? There's some threshold above which I care about, and maybe that threshold is 0. And I say, is the number 17 at least 0? And if the answer is yes, well, then we'll go ahead and put a 1 in the output neuron. And if the answer were no, well, then it would be a 0, for example. And so this is the math, then, that our neural network is doing. And we could take a different example. If this weight over here wasn't a positive 2, but instead it were, say, negative 2, what would the math look like? Well, we'd still take 4 and multiply it by 1 and get 4. This time we take 5 and multiply it by negative 2, and we'd get negative 10 as a result. Then add those values together, add in our bias. So we do 4 plus negative 10 plus 3. We get an answer of negative 3. And is that at least 0? Well, no, negative 3 is less than 0. And so the output is going to be, in this case, a 0. So you can see that depending on how we choose the weights and the bias in this case, our choices of weights and biases determines how the neural network works. We get a different answer to our question, yes or no, 1 or 0, depending on what the values of the weights and biases are. And so what the neural network is going to try to do is come up with good values for these weights and biases so that it can try and make some kind of a good prediction. I'll take a brief break and then pick up from there. But how does a neural network actually learn those weights and biases? We've talked about it needs to learn those weights and biases to be able to make good predictions. But what does that process actually look like? Well, ultimately, it again comes down to that training data. The training data is the information that we're using to give to the AI. And we give it to the AI, and it uses that training data to figure out what the weights and biases should be. And so we'll take a look at an example of what that might look like. Let's imagine that we ran this neural network. We provided it with these inputs. It predicted an output of 0. So that was the predicted value that was given to us by the neural network. But maybe based on our training data, the actual value, the value that it should have predicted, was a 1. So this neural network didn't really do a very good job because the actual value that it was supposed to predict was 1. But in this case, it predicted a 0. Well, based on that training example, we can have the AI learn from that experience. We can have the AI say, you know what, these weights and biases, maybe they're not totally correct because they didn't do a good job of predicting in this case. Maybe I need to adjust those weights and biases a little bit. And so after we run through a training example, what we can say is, you know what, take these weights and biases and adjust them a little bit so that it does a better job of trying to predict this value in the future for this particular example. And if we do that, maybe not just for one data point, but for many data points, and repeat that across many, many iterations, if every time we give the AI an example, it runs through the neural network, it tries to make a prediction, and based on the result of that, it learns how to adjust ever so slightly. It adjusts the weights a little bit every time, iteratively getting better and better at making predictions for every example, then the hope is that by the end of that process, by the end of the training process, we have a neural network that has weights and biases that are going to do a good job of making a prediction, that have learned something about the relationship between all of those input values and that output value to be able to make that prediction well. But ultimately what it's doing, the ultimate equation that our AI is engaging in, is really just this calculation here. We're taking all of the input values, adding them together by multiplying them first based on their weights, and we're using that information to try and make a prediction as well. So that then is the idea of what our neural network is doing and the kinds of patterns that it's trying to learn. And we can imagine what this would look like as we try and learn more sophisticated patterns, as we try and classify data that looks in different forms. And so let's take a look at some more data. Let's imagine sorry, let me back up. Yeah, I can start from the center. Sorry, give me a moment to think. OK, so it's calculating this equation here in order to make good predictions. All right, we'll continue from there. Yeah, I'll pick up from here. So let's take a look at what a neural network might actually be learning and visualize the pattern that it's actually seeing once it's taken some data and it's tried to learn some patterns from that data. So we'll go ahead and represent it again using a graph here. And imagine that we're taking two variables and we're trying to predict two categories, like the blue dots and the red dots, for example. What a neural network is ultimately calculating, at least in this case, would be something like a line, some line like this where we're saying, you know what, all the blue points belong on this side of the line, all the red points belong on that side of the line, for example. And so it's making this classification, dividing the world into these two categories, the blue category and the red category, for example. But in some cases, it's not going to be so simple. It's not going to be as easy as just saying, draw a line and separate things on one side versus the other. For example, let's take a look at data like this. Here I've got two blue points and I've got two red points. And my question for you is, can you draw a line through this data in such a way that all the blue points are on one side of the line and all the red points are on the other side of the line? And you might try to do it. You might try a few different lines. But it turns out to be a hard thing to do. It turns out there's actually no way to do it. Any line I draw, I can't make it so that only the blues are on one side and only the reds are on the other side. It's going to be, at least on one side, some kind of a mix of them. You know, I might try to draw the line this way, but that doesn't quite work. If I draw the line that way, I still have red and blue on the same side here. And so ultimately, we're running into a little bit of a problem, which is just that simple equation of just taking weights, multiplying them by their input values, adding in the bias at the end. That's what we might call a linear equation. And a linear equation is really just drawing a line or something like a line in higher dimensions, for example. And so there are some patterns that are going to be harder for a neural network to be able to work with if we're just dealing with that single layer of the neural network, that single calculation that we're performing. So how are we going to solve that problem? Well, ultimately, we can solve that problem by introducing more layers to the neural network that are performing some transformations on their inputs in order to make sure that we can get some more sophisticated kinds of output here. So rather than just having these input neurons over here on the left and a single output neuron that all of these are connected to each other, we might introduce another layer to the neural network in between, this layer in the middle that we might call a hidden layer of this neural network, where we have all of the inputs connected to this hidden layer. And then we have all of those values, all of those neurons, connected to the output too. And what's going on here is a similar process. Each connection here represents some weight that describes how much does this value, the neuron's value over here, affect the neuron's value for this neuron over here, and so on and so forth for all of those other connections. And then we can do those kinds of transformations where we say, is the value at least a threshold of 0 by, calculating all of these values? Or we can also perform other kinds of transformations as well. There are different ways of trying to design these kinds of neural networks. But by building these larger networks that are performing more of these kinds of transformations, we can start to learn some more sophisticated patterns. And if you hear about neural networks nowadays that have millions or even billions or trillions of parameters, this is the kind of thing they're thinking about, is they have many of these different connections between many of these different neurons. Sometimes we don't just have 3 layers, but we have even more layers to these neural networks as well that allow these neural networks to learn these very sophisticated patterns where each one of these connections just represents a very, very small piece of information about the relationship between 2 values. But taken all together, we can end up using them to make some really valuable, useful predictions as a result too. And so that then is what it might look like to create a multi-layer neural network. And in the end, our multi-layer neural network might still be trying to predict some classification output, like yes or no, or we might use a 0 to say, no, it doesn't belong in this category, maybe a 1 to say, maybe yes, it does belong in those categories. But so far, these examples that we've been talking about have been, again, what we call binary classification, where we're taking some piece of data and we're grouping it into 2 categories. We're saying, yes, it's raining, or no, it's not raining. Or yes, this is a spam phone call, or no, it's not a spam phone call. But classification often goes beyond just 2 categories, for example. We might have more categories. Maybe we have 3 or 4 or 5 categories, for instance. And we still want to be able to make some kind of a classification. Like if you get a text message and you want to say, is this a normal text message, or is it a spam text message, or is this like a priority text message that I should really pay attention to? That might be an example of dividing things into more than just 2 categories. Or if I'm categorizing my clothes, maybe I don't just want to categorize into summer and winter clothes, but I want different boxes for all the different seasons, for instance. So you might reasonably have more than just 2 categories that you're trying to use in order to perform that classification. But what then would that look like if you were to translate that into a neural network, where so far we said the neural network is just going to predict as output like 0 or 1, 0 for belonging in one category, 1 for belonging in another category. Now you could say, you know what, let's have the output be like 0, 1, or 2, where we say that it's going to be 0 for one category, 1 for another category, 2 for a third category after that. That could be one way you construct this neural network. But that would imply some kind of ordering between all the output values, that maybe 1 and 2 are closer together than 0 and 2 are to each other. And that might not always be the case. Often you have these different categories where you might not know which categories are closer together than other categories. And so you don't just want one output to be like 0, 1, or 2. If I want to group something into 3 different categories, then instead of just having one output, maybe instead I'll have 3 different outputs. Or if I'm trying to group something into category A or category B or category C, then I have 3 output neurons for this neural network, 1 representing the first category, 1 representing the second category, and 1 representing the third category. And what the neural network might do then is, as it performs its calculation, what the output might be is some kind of a probability. How likely is it that this input falls into one category or the second or the third? So you might end up with output that looks a little something like this, where we say, you know what, I think there is a 60% chance that this input belongs to the first category, a 15% chance it belongs to the second category, and a 25% chance that it belongs to the third. So that way our neural network is learning how to predict which of the 3 categories it belongs to. And based on the output, you can get a sense for how confident does the AI feel in its answer, how likely is it one thing versus another thing, and that might be useful information for you to know as well. So we can expand this neural network idea, change the number of these units that happen to exist in each of the layers, change the size of the input, and change the size of the output, depending on the problem that we're trying to solve. But through all of these examples, we have to remember that what it's doing is making a prediction, that it's making a prediction. It said like there was, a 60% chance it belongs to one category. And so as a result, we have to treat these neural networks very differently than we treated examples like the calculator example that we started with, where this calculator was deterministic. You give this calculator a math equation, and it's going to get the right answer. You don't have to worry about the fact, like, is it guessing what it thinks the right answer might be? It's always following the exact same steps. It's always going to get a particular answer. Whereas these neural networks, they're trained based on training data. They're trained to try and produce an accurate prediction, but it's not going to produce an accurate prediction all the time. Sometimes the AI is going to be wrong. Sometimes it's going to produce some kind of an error. And we, as the people using and designing these kinds of AI systems, need to be mindful of that and decide how we're going to deal with that. We have to treat AI a little bit differently, acknowledging the fact that it might end up generating these errors, and decide how we want to do it, decide how much we want to trust AI in any given situation, because we don't know. Sometimes it might be right, but sometimes it might be wrong too. And so we need to be able to be aware of and think about those implications too. But even though AI can still make errors, it is still useful for being able to make predictions, for being able to predict something about the world, learning from data, and being able to tell us something useful. And so hopefully you get a better sense now for how AI can be used in order to make those kinds of predictions. And next time we'll take a look even more at how we can give AI some data, have it analyze that data, and do something useful for us with that data too. So we'll see you next time.